So first, let me introduce you to Sarah and the secure internet connectivity. So we're going to start off with a narrative of Sarah, and she's trying to gain access to a secure system. So meet Sarah. Sarah is writing a Kubernetes application that is going to be deployed into the public cloud, and one of her pods in her application needs secure access to her corporate intranet. And before we get too far along as well, if anyone has any questions, feel free to ask during the session as well. So I know there's a couple microphones, because if you have a question on it, then other people may have a question as well. So ask questions. So from Sarah's point of view, this is what her needs are. She wants to have this secure system going to her corporate intranet, but at the same time, she still wants to have her Kubernetes networking untouched. So, and specifically, there's something called secure here that she wants. She doesn't really know too much about it. She just knows that that connection needs to be secure as well. So this is her path. First, she has to work out what subnet does her network interface need to connect to. So she discovers a subnet, but who defines that subnet? Is that her responsibility? Is it an operator somewhere? And what if she defines a subnet? What if it's too small? Like, what does she do in the future? Does she have to also define the subnet that goes, or the interface that goes from the subnet to the VPN gateway, or is that someone else's job? And then she has to take the routes from her VPN gateway that's provided, and then how does she insert those routes into the pod? Now, one thing about adding routes to a pod is it requires you to be privileged, which means that you don't generally want to run your pod as privileged, and so there's also a mismatch with Kubernetes. So what if the subnet is finally too small and she needs more replicas, then does she have to redo this subnet again? Or if the subnet itself changes, there's some new details that come in, does she have to change both of these interfaces? Let's say that the enterprise team comes in and says, hey, your subnet you chose a subnet like months ago that's now incompatible with our corporate intranet. So you're going to have to change. So does that mean she has to redefine all of this again? Short answer is yes at this point. Or they decide to re-IP, same problem. So you also have a new CEDAR route that goes into the corporate networks. Time to update the routes again. So suppose that the IT now says in order to connect your pod up, they want you to have a firewall, and that firewall has to sit on your subnet before it goes into the VPN gateway pod. So that means she has to redo this all again as well. So she asks the question, why am I doing design with 1990s concepts? And trying to pigeonhole it into Kubernetes. So we have our mascot, Ariadne, who is here to help. So Ariadne is the NSM network service mesh spider with a strong relation to the Greek mythology version. So anyways, she says, well, what is network service mesh? Is that like Istio? So we're not here to talk about Istio, but we took some interesting ideas from Istio. And so basically, Istio is layer 4 through layer 7, and it will manage network connections, so specifically TCP streams for you. So we're trying to do that, but instead of doing an L4 and L7 that you would typically see in your standard service mesh, we're going to apply those concepts to L2 and L3 to get you things like VPN, or maybe you need Ethernet or MPLS or access to some hardware. Sure.
So what's the difference between Istio and Envoy? I heard that CNCF has the Envoy, which is doing the same thing. So are they equivalent? Are they different?
Okay, so that's a good question. So the question is, what is the difference between Istio and Envoy? So, and there is an application to this. So Envoy is an application that makes use. It's effectively a proxy. It's a smart proxy. Istio is a system that configures Envoy to act in a specific way. So Istio uses Envoy. Envoy is layer 4, is typically layer 4 and layer 7. So again, TCP traffic and some smart things on a protocol. So if you're doing HTTP or so on, then Envoy can help you with that. We're working at a level lower, so we're looking at layer 2 and layer 3. So what happens before that TCP stream is even really a thing? How do you get that connectivity? So that's the main difference. So there is a nice play that I'm trying to organize with some of the people from Envoy and Istio, where I want, like, Istio might say, we want to span across multiple VPNs. But rather than go through all of the trouble of setting up all the VPN and manage all that system, I'm in contact with some of their developers, and I'm trying to work out if we can do something with that. But that's an advanced topic. We can come back to that. Just know that. Sorry, one other question?
Question right on it, sort of out of the line here, but does Istio need Envoy, or does Envoy need Istio?
So Istio needs, we'll say needs in a light way.
Sidecar, besides the sidecar, do they share anything else?
Well, Istio uses Envoy heavily. So right now, Istio's architecture has Envoy has a important concept.
Envoy before you install Istio.
Well, Istio should install it for you. So when you install Istio, it'll install Envoy as a component. So, cool. Okay, so going back to our narrative, Sarah says to Ariadne, I have a pod. I just want to securely connect to my corporate internet. Like, that is the thing that she wants. So this is how we do it within Network Service Mesh. So this is YAML, and I apologize for the I need to work out why it's mangling my YAML. But it says, so you give it a network service. The network service, the name is Secure Internet Connectivity. And the payload is IP. So we're going to say, layer 3. So this borrows a lot from service resources within Kubernetes. So you could use, the same way you have selectors on pods or so on, you expose a network service, and instead of exposing a port, like port 480 or port 443, you expose a payload, and that payload could be like TCP, or payload could be like IP or Ethernet or MPLS or so on. Sure.
Where does this network service configuration reside?
Good question. So this gets created as a CRD, custom resource definition within Kubernetes. So Kubernetes has a database inside of it that you can create custom data types, and so we store this network service within that, and it acts as a registry. So you'll see more on that in the architecture when we progress. So in this particular scenario, what she needs to do is she would have the system will have an init container and a config map. And so the init container is just something to request for it. The init container, a difference between Envoy, and this will change in Envoy in the near future, but the main difference between today's Envoy and the network service mesh way of getting things into your pod is that network service mesh does not require privileges in order to get in. So it'll ask for the thing that it wants, and then that init container will then we'll ask for it. Then there's a privileged container somewhere else that is not part of this workflow, that is not controllable by the user, that can then inject that interface in, and we'll see how that works again in a short while. So things to notice about this: there's no definition of interfaces, there's no subnets, no routes that are listed in here. So in Sarah's perspective, it looks a little bit like magic. So you've already been introduced with the first two basic concepts. So we have three basic concepts with a network service, that I guess you say three primitives. So the first one is the thing that you want, the network service. We call it network service itself. So you have, in this scenario, the network service is secure internet connectivity. And that secure internet connectivity is implemented by a network service endpoint. So that endpoint is, in this scenario, a pod that provides the concrete thing that provides that network service. So it's very analogous to endpoints in Kubernetes, where you have like a service that's been exposed, and you can have multiple pods that provide that. So it's a similar concept. Sure.
Does Sarah have her own network namespace?
Yeah, so all pods have a network namespace as part of its definition. So yeah, Sarah would have a network namespace for herself. So
she only gets one pod?
well, she can spin up as many pods as she like, and then they can all request for connectivity into it. So, and then each of those will get an interface into the system. So, the second thing is Sarah as a client, like her client making a request. The third concept that we have is the connection, and that's the connection between Sarah's pod and the VPN gateway pod. Now, one important thing is that the interface itself is not the major concept, even though we do work with interfaces. So usually, the most interfaces that you'll see in Kubernetes are going to be kernel interfaces. But we also have users who want something that's a little bit more complex, a little bit more exotic. So things like, in VPP, you have things like memIF, or if you're working with OVS, you have things like vhost user. So we can inject in those types of interfaces, which allow you to do kernel bypass and get very fast connectivity to your data plane. But in Sarah's case, she just wants a kernel interface. So in terms of subnets, also all connections, there is no subnet that's listed here. So all connections within network service mesh are point to point. If you want a subnet, that is a network service. If you want a bridge domain, that's a network service. So that's another key difference. So most SDNs, if you look at them, the SDNs are actually, the primitive is the subnet. Like you bring up Neutron. Neutron, you create the network, and then you create ports on that network, and you attach yourself to that port. So in this scenario, the bridge domain or the subnet is not the primitive. The subnet is a network service. So it's one critical difference in the data model. And routes get injected in through context. So as part of the message, it'll say, here are the routes, and they'll get injected in. So in terms of a firewall, so this is where we get to a mesh part. So suppose she needs a firewall. So the firewall, all she sees is a secure internet connectivity. But inside of this, the secure internet connectivity contains a firewall pod and a VPN pod, and all of the connections in between. So the way that this works is very similar to virtual host and route rules within Istio. So we extend the concept to an L2, L3 environment. So we start off by giving labels. So we have a label on the firewall pod. In this scenario, we'll say the label is called app equal firewall, and the VPN gateway itself has a label as well. We'll say app equal VPN gateway. So when the firewall wants to connect to the VPN gateway pod, it connects to secure internet connectivity. And it has a selector. The selector in this scenario, the source is app firewall. The destination is VPN gateway. And let's see, I lost my video. Give me a second. Okay, we're back. So in that scenario, when you connect them, when the firewall says, please connect me to secure internet connectivity, it matches that and then creates the connection between the two.
Don't you have to have some ingress pod there also?
The question is about an Ingress pod. So in this scenario, network service mesh is orthogonal to Kubernetes networking. So things like Ingress pods or Ingress routes or so on don't really make as much sense in this scenario. Although you could implement those type of concepts in, but that would be a level higher from network service mesh with someone implementing that as a feature. So for the pod getting into the firewall, we have the default matcher, and what we do is we say the default match is see, there's no source selector, so the default in this scenario is destination app is firewall. So Sarah's pod in this scenario, since it has no relevant labels, gets matched up to the app firewall and that completes the full connection from the pod to the firewall to the VPN gateway. So if IT decides to put something else, let's say they decide to put on a content filter or load balance across multiple VPN gateways or so on, Sarah doesn't have to worry about any of that. The operator is able to create these as part of the network service and fix the wiring, and then Sarah will then gain these properties as part of just connecting to secure internet connectivity.
Only for middle box services, right?
The question is this on?
Services you are defining as a service, network as a service. What you are defining, these are middle box services, not the end application.
So I can only hear part of the question. So you're asking if they're only middle boxes?
Yes.
So no, they don't have to only be middle boxes. They can also be things that you want to connect to at an edge as well. I think that middle boxes are a bit of it, like bumps in the wire, firewalls, and similar things are the first easy targets. But there's no reason why the thing that you're trying to connect to can't be some destination thing as well. Like, give me access to that refrigerator, or give me access to that IoT device over there. So there is a possibility to do that. But most of our narratives are focused on this, since it's easier to drive this at this point. Another question.
So what is the network service? It's a special port with some labels, or?
So the network service itself is the whole set of things that you want to like. What is the thing that Sarah actually wants? So Sarah doesn't really want a firewall or VPN gateway. She actually doesn't care about any of that stuff. What she cares about is that she has something that will give her connectivity to her secure internet.
Is it your IP who implements these services, or it's coming from the network service mesh?
It could be either. So it could be IT, it could be someone in operations, it could be a mixture of both. So you could have your IT might set up the VPN concentrator that you're connecting to. Your operator, your Kubernetes operator, might set up the VPN gateway pod for you and the firewall for you, and have them configured to work with each other. So you can actually have multiple players, multiple actors in this scenario. We don't cover that in this presentation for two reasons. Number one is it's more complex from a narrative perspective. The second thing is that we're in the process of working out some of the authentication. So if you have an interest in helping with that, we can totally use some help working out the proper way to perform authentication. And not just between Kubernetes systems, which is a relatively easy problem. It's actually, how do you perform authentication across all sorts of disparate systems in a way that still has trust. So we're going to aim for the slightly harder problem, but yeah, any help in that would be useful if you have an interest. So some things to notice: we still haven't spoken about IPs, subnets, routes, or interfaces within any of this stuff. So we will get to them, but just notice that these concepts don't have this set up. Also, it does not require a special version of Kubernetes, so that's one thing that we have to be very careful with, is we don't want people to have to compile their own custom Kubernetes or compile their own special CNI in order to get a hold of this, because people already have their Kubernetes instances that they're running with or have been certified by their vendor, and they have their CNI plugins the same way, have been certified by their vendor, or they're happy using Calico or Weave or whatever it is they're using. So we don't want to replace that. Instead, we complement. So, sure.
You mentioned the kernel interfaces and manif and stuff like that. So how generic hosts have or need?
So can you ask the question one more time? It's hard to hear.
So how generic or how specific are the hosts to the services?
So the question is, how specific is the host to a specific service? So we'll see in a presentation in a few moments that the pod will when it makes a request, will tell the network service mesh what its capabilities are. So if you bring a pod that has memIF, or you bring a pod that speaks vhost user, it'll tell it. And then it'll negotiate. You also tell its list of preferences. So if you support all three, but you prefer memIF, vhost user, kernel in that way, then you can control that as the pod connecting in, and that gets negotiated based upon the capabilities of your data plane, the capabilities of your pod. And we'll see an example of this in a few moments. So how does that use case work? So what we do is we have a network service manager. So we follow, I actually don't know how to pronounce his name properly, but Phil Calcado, I'll guess. So we follow his paper and his approach. And so if you look at something like how Envoy works, so we have a network service manager that runs as a daemon set. And so every node will have one network service manager attached to it. So in this scenario, we have a node, and then a network service manager, and we have a data plane. So one key difference as well is that we actually don't provide the data plane itself, but rather we work with a data plane. So if you bring vhost user, you bring OVS or whatever it is that you want, you should be able to gain interactivity with that. So we're working with data plane providers in order to increase the number of data planes that we're working with. So how does all this work? So we start off with a request connection. Now we have an init container in this scenario. You don't actually have to run the init container. You could speak the network service mesh client API yourself. So that means if you want to do something that's a bit smarter, then you don't have to use the init container. But Sarah's pod just wants to keep it simple. So we say there's an init container that'll perform the call for her. So this goes over a Unix socket to the network service mesh daemon. So this Unix socket, we know exactly which pod owns that Unix socket. So any requests that come in, we know exactly who's making the request. So that also eliminates or reduces the possibility of someone spoofing or saying, hey, I'm someone else. We can verify who they are. So they'll request a connection. And so the type of thing, what's inside of the interface is what is it that you want to connect to? And additional properties for your system, like I want a kernel interface. I want that interface to have this name or other additional information that you would want in it. So let's talk with the first scenario where your VPN gateway pod is on the same node. So what happens is this request gets sent to the VPN gateway pod, and which then responds. It replies saying, yes, I can take this connection, or no, I can't. And let's assume that the connection was successful. And then a interface is created and injected into your data plane and connects your VPN gateway pod. And then it creates and injects the interface within the client pod inside of Sarah's pod. And then it creates a point-to-point tunnel or point-to-point connection within the data plane, which completes the cross-connect. And finally, it responds back to the client saying that the connection is up and ready to go. So that way you don't have a client that thinks it has access to a network when it's not ready yet. So this is the single node use case.
How different than CNI plugin?
Okay, so what the CNI plugin does is it's a very, very specific thing. CNI is asking you to connect you to a specific kind of network. So it's asking you, most people when they say I want to run CNI, they want to connect up to a Kubernetes network that's abstracted at an L3 layer, and they want attached to that ingress policy, egress policy, and service routing. So all that combined together is effectively what CNI provides you as one giant box. So network service mesh is you can define the type of things that you want. So so in this scenario, we have the firewall, the VPN gateway, and so on. So the primary difference is in, I guess you would say, part of it is in flexibility. The second thing is that when CNI runs in Kubernetes, it can only load in kernel interfaces. It's not able to load in memif or vhost user or so on. And the reason why is when CNI runs, CNI only has access to the network namespace. And in order to drop in shared memory, you need to be able to mount that shared memory somewhere. So what typically happens is you mount the shared memory has an inode, and that inode then is mounted into the file system so that way you can start manipulating your shared memory path. But there's no file system to mount the inode to, so there's no way for CNI to communicate that to the pod. What's the question?
So the next question is this NSMT, this network service container, whatever you call, is it the runtime of that is which side? This side or this side?
Oh, networks.
Running
So Network Service Manager does a couple things. It handles the negotiation. It's a process. It's a pod that manages the connections, the network service mesh connections within that system. So all pods communicate with that want to use network service mesh communicate with the network service manager, and it handles the requests and responses and for both the clients and the endpoints on that system, and also coordinates with the data plane. So there's 3 things that it ends up communicating with in that scenario.
My question was, this looks something like a SIP server.
Okay.
So you initiate something and then you get some proxy and then so the middle portion is the runtime.
Right.
Whether it resides on the client side, server side, if I take those 2 pieces, one is the service provider, one is the client. In between, where does it sit? Either side?
So,
You have to figure out where is it.
so I don't know how to mix that into a simple question. So I'm gonna try to answer. So this NSM manager is the centralized system for that node. So there's no client network service manager. There's no server endpoint network service manager or no data plane network service manager. So it's one collection of processes that are designed to manage everything within that node that has to do with network service mesh. So there's
So both sides there are pods.
right.
In between part, does it belong to this pod, that pod?
Neither. It's its own thing. It's unique. You know,
It's a unique one.
yeah, and there's only
It's its own namespace. basically.
yeah, it has its own namespace, has its own, and it communicates with other pods on the system, but it itself is a unique pod on that system that handles all requests.
So it provides the shared memory for both of them.
Correct. Well, yeah, we'll say it does in that scenario. It's a little bit more complex, but in the model, that's what it looks like. And so,
Do you have to run the network services on every node where there is a client for that given service?
that's a good question. So the question is, you have to run the network service for every network service endpoint for that specific thing on everywhere in the same node as the clients. So in other words, like, do you have to run, if you have a cluster of like 100 systems, do you have to run a 100 VPN gateway pods? No, you don't. So you'll see in the next example that we actually have multi node example. So,
Question?
sure.
In the data plane kernel view switch, is that a Docker switch or is it a Linux
Oh,
switch or?
that the data.
Any of those or?
The data plane can be all of those or any of those and more. So actually, our API that we speak is generic, and so it could be a kernel-based switch. It could be a user space switch you bring. We could pair you up with some hardware top of rack switch if you choose to do so. So it's very flexible in that model. Cool. So what happens if the VPN gateway pod is on a different node? So it looks very similar to what we had before. In this scenario, though, we have a network service manager on each node. So we have one on node 1, one on node 2. And also we have multiple data planes as well. So in this scenario, we ask for a network service endpoint, the list of network service endpoints that are exposed a specific network service. And that response goes back to the network service manager. So the network service manager says, oh, I have a request for a connection for secure internet connectivity. And in this scenario, VPN gateway pod. Who owns a VPN gateway pod? And so in this scenario, node 2 owns it. So what it'll do is it'll make the request to the network service manager of that node. But it also adds in additional things as well. So this data plane will have certain capabilities. Like it might say, I can speak VXLAN and GRE, and these are my preferences for my parameters. So it'll pass that information to the second network service manager on the system. So you have the standard requests and responses as we had before. The interface gets injected in as it did before. The right-hand side of the tunnel gets created, and that's where the parameters are also chosen. So it'll say, okay, I selected VXLAN with these parameters. And those parameters are then sent back to the network service manager of the first node, which is then injects the interface and then configures the data plane on the left side in order to complete the tunnel. So we got some questions. So first I saw that hand come up.
If you don't use a network service mesh, how people do today with Flannel, with archive solutions?
Okay, so the thing to remember on Flannel is designed to do one very specific thing. That's to provide you with Kubernetes networking for a single host, or not for a single host, for a single cluster. So if you want to do things beyond that, it's not natural for Flannel to provide those type of things. So in the way that Flannel, it depends on the backing system for Flannel, but typically a lot of the parameters, if I recall properly, end up in etcd. And so they'll try to manage some of the stuff within etcd that's like what host owns what subnet and what host, how do you connect to it, depending on your provider. There was another question here. Yep.
So since with Istio, we're already running the Envoy sidecar proxy.
Right.
Would it not be possible to implement the kind of use cases of network service manager in Envoy itself?
Okay. So the question is, would it be possible to run these type of things with Envoy rather than network service mesh? So there is possibility to mix in some of this capability, but the problem is that when you start looking at lower level scenarios, there's some contention when you start to implement like L2, L3 versus like 4 and 7, and more specifically, Envoy is designed specifically to handle TCP streams. So what happens if the thing that you want ends up becoming like you want it to be MPLS or DOCSIS or something else? Like, does TCP even make sense in those scenarios? So Envoy would have to change significantly in order to make all that work. Well, IPv6 is just another payload for us. So yeah, so it could be IPv6 that you want to run. That's a question? So the question is about how the information is transferred. Like, how does who? Well, for building up the tunnel. So there's a couple APIs that we have. So first is with the step 3 request connection. Will pass information about the data plane and its capabilities and preferred. On the yeah, it's a negotiation. On the response, the negotiation has been it responds back with, these are the parameters that I've chosen for you. So there's actually, in the case of VXLAN, most people think of them as the VNI, like you want to make the VNI a certain number and then you want to have all hosts for that bridge domain try to connect to that specific VNI. Because we're doing point-to-point connections, we actually do a tuple on 3. So it's not just the VNI, we also do source, destination, and VNI. So there's no chance of us running out of VNIs as a possibility. And that's a significant advantage that we gained by moving away from the concept of your subnet or your bridge domain being the thing that is your primitive. So when it comes to, sure, what's the question?
Yeah, how does in step 3? How does MSMT1 find MSE2?
So in step 2, it's asking for who provides these network services. So step 2 this is actually.
Step 2 gives the address of MSMT2.
That's correct.
MSE1.
That's correct. And there's another step.
Domain, or is that a numerical address?
It could be either one. Right now we're working primarily with numerical addresses, but there's no reason why it can't be a domain. Sorry, let me go with this one on first. Well, can you speak up?
How much memory?
So how much memory does all this take? It should be relatively low. I need to profile it to give you an exact amount, but it should be relatively low. Like, we implemented it in Go. We were trying to use best practices for this. in terms of the data we have to store, there's not a huge amount of data that needs to be stored. We find that the bigger thing is that takes up resources is actually going to be the data plane. So cool. And then we had.
So go back to the question why we cannot put in the Envoy, right? The NSM is, for me, it's a lot of overlapping with Envoy. The only thing Envoy cannot do today is to establish the GIE or EXAM tunnel. The ROS communication step 1, 2, 3, 4, I think Envoy can do it. Just make some minor change on Envoy, right?
Yeah, so it is possible that you could try to set it up like that so that Envoy handles it, but the thing that we're looking at is before Envoy can even talk, so I'll use the same example I used with Istio. Before Istio can even make a connection, you have to establish your underlay first. And so this is a system that's capable of establishing that underlay. So before Envoy is able to make those type of connections, that's part of what we're aiming for. One question back.
Continuing on that, like one of the nice things about Istio and the use of Envoy sidecars is that all remote connections essentially get instantiated through the Envoy pod.
Right.
Sidecar pod. So is there a possibility for the connection request to be done not by Sarah's pod but by the Envoy pod?
Yeah, that's a possibility. So the question is it possible for, like, if you had an Envoy pod, could you have Envoy pod make other requests out for other types of connections? Short answer is yes, and that's actually something that I'm aiming to do. There's some interesting use cases that can come up, like maybe you want to have Envoy connect to some VPN-based system somewhere else, and how do you establish in that connection? You could have the Envoy pod make that network service mesh connection on your behalf. So that is a potential use case.
So the API server gets the address of MSV2 from the UTCD?
Yeah, well, it's basically from Kubernetes API server, which is typically backed by etcd. Not required to be etcd, but yeah, it's typically yes. So cool. So let me finish up this example because we have a limited amount of time and we have some hands-on stuff to go through as well. So just to finish this off, so we have the tunnel created as we described. Then it responds back saying you're ready to go, and then you're up and then you're connected. So in that scenario, so this is like the workflow in a nutshell. See, there's one other thing as well. I don't have a slide for it. So the last component that ties to what you're asking about before is how do you know where this network service endpoint is? You spin up this pod. How do you know where it is in the first place? So when this pod spins up, it registers with the network service mesh daemon using that Unix socket that we described before, and then the network service manager will then publish that endpoint to the Kubernetes API server. And that information contains what's the network service manager that's facilitating it, and what's the name of the endpoint that you're trying to connect to, and then network service manager then will complete the rest. So cool. So let's move over towards doing a demo. So if you would like to give this a try as well, I've spun up a bunch of systems, so if you have a computer available, you're able to log in and use them. So the information, if you go to networkservicemesh.io, and I'll ask in a while if it's large enough so I can see about increasing it. But if in the very top you have documentation, sorry, not the documentation, you have events. And we have the out-of-the-box networking event on here, and I have a link here called live root. So do root at. So these are actually physical boxes, so they're not VMs. By the way, these servers are provided by CNCF and Packet, so thanks to them for providing this stuff. Okay, so.
Is that something you need to, whenever you're working on it, so it's a bare metal system, right? They do bare metal stuff.
Yeah, these ones are bare metal.
So you are not using, you normally save it and then switch it off, or how is it? Because the billing is continuous, right?
Oh, that's fine. These ones are 50 cents an hour.
I see.
And we're actually going to spin up 3 Kubernetes nodes in each one. So we have you'll see how that's done in a moment. Okay, so now that you're connected in, I'll go ahead and connect to mine, and let's see if I can expand that out. And okay, so let me go ahead and make sure I get the. Since I told you all to do this, let me copy this entire thing. And so with that, I'm logged in. So the first thing to do is make sure that you have some of the relevant tools installed. So it's possible. I want to make sure I didn't misconfigure your system. So for checking what tools are involved, first make sure Go is installed just by typing Go and hitting Enter. So if Go is not installed, let me know. Okay. The second thing we're going to check is to make sure that Kind is installed. So if it's not installed, so it doesn't work on my particular system. Is your system broken? Okay, so for setting up Kind, what we need is, I think I said I'll copy and paste some of this stuff so that you can see it there. So if it doesn't work, that's the command that you want to run, and then run Kind again. And so I've added it to the Etherpad. So what this does is it sets up the Go binary. So when I install Kind, it installs it to the home directory /go/bin by default. So that needs to be in your path. So was someone able to verify that Kind works? Cool, Kind works. So the next thing to do is we're going to verify that Docker is working. So run Docker version and get rid of the dash no. So you run Docker version, and you should see both client and an engine. So can someone verify that it works on your system? This does not work? Okay. What's the error message that you're saying? Well, what, are you saying you're saying the client side but not the server?
I just typed Docker.
Didn't find it? Okay. So I'll type in the command to install it, and then you can run the command. So if it's not working on your systems, the command to install it is posted. So I posted into the Etherpad if you want to gain access to it or to. Yeah, that'll do it. So in that scenario, you can just log out and log back in again. It should be, and then check to see if Docker version works for you. After you run the Kind one, if Kind is not there. So you can copy and paste my on my Etherpad. So okay, and the last thing to verify is also going to be kube control. So that's, let me see if I can expand this out. So I'm a very new Mac user, so please excuse me. I've only had this for like a month or so. So is your Docker working now? Okay, can you run kube control as well? Make sure kube control works? Cool. So what we're going to do now is we're going to CD into network service mesh. So also, let me make sure. Can you all read this in the back? Cool. So So this particular system, we're going to start up Kubernetes. So the way you start up Kubernetes is you run make kind-start. And when you run that, then it'll start up a Kubernetes system for you. So let me delete my cluster and spin it up again so I can do it all with you. Okay, and so what this is doing is it's installing in Docker. It's creating 3 Docker containers, and inside of them are three Kubernetes nodes. And so those nodes, you'll be able to treat them as individual systems. So this actually is really useful. If you're doing Docker development, I highly recommend that you get kind installed on your system and learn how to use it. So it allows you to spin up multiple clusters, keep them isolated, and so on. So while that's running, let's take a look at some of the things that we're going to be using. So let me see. View. I want to make sure I can expand this. Does anyone know the commands in order to increase the font size on this by any chance? Take that as a no. Okay, so what I'll do is I'll open up I should have ran it in tmux so I can pull it out, but I'll just pull out the IP address and so what we're going to look at is in network service mesh. We're going to look at first how do you. So this is for development systems. We have a set of various tasks that you're able to run. So we have the ability to start a cluster, stop a cluster. We can start or stop on packet. In the near future, we'll be able to start on GKE, so you'll be able to try those out. You have to provide your own credentials for those, but it allows you to set all that up. So in this scenario, the one that we're going to look at first is the infra deploy. So this is actually what will install Kubernetes, is that Kubernetes-infra-deploy. Let's wait for the scene to finish up. So I've already built the Docker containers for this particular system. Once this is up and running, what we'll want to do is we'll want to kick off the install. So I'm not going to run it again at this particular point, but you can run Kubernetes save, and that's what you use in order to create all the images for Kubernetes. So now we have in here. So kind just completed. So we have kubectl, and we can say kubectl get nodes. Let's see. Oh, that's right. I forgot to run the kubeconfig. So we want to run kubeconfig. I'll add that to the Etherpad. Okay, it's already added in. And the second thing you want to run is also the export cluster rules. So this is how you tell it, like how you tell the build system that you want to test against kind or GKE or packet or nothing. Use your own kubectl that's already been provided. So now that we have that, so the command to start it is make Kubernetes infra deploy. So we'll go ahead and run that. And while that is running, we'll go into the second screen and we'll see, let's see, export, that's right, export path equal. So we can see that there's, the pods are starting to be installed. So So it's loading the image for each one of these. It's starting to load the image to Kubernetes, and we can see that they're starting to come up. So this takes about a minute or so to come online. So let me reduce these. So the Vpp data, this particular one is probably the largest one. So this is actually what eats up most of the time. This package is actually closer to 700 megs or so. Okay, once this is installed, so I'm going to show off two particular use cases. So the first use case is going to be a simple hello world ICMP responder. The second use case is going to be a VPN gateway that has, or a VPN style example, but it's actually going to show off the firewall. So we're going to actually have something in the middle that installs the firewall. Okay, and let's just wait for pods to finish starting up. So the last ones we're waiting for just the skydive. So skydive is the visualization, topology visualization that I mentioned before. So while it's running, so let me go and show you some of the examples. So we have, inside of the examples, we have a Kubernetes directory. And so we'll look at the client first. And the client is incredibly simple, so you'll see what that looks like. So in this scenario, we have a label. So inside of the metadata, so you notice that our container we're using is just a standard outline. There's nothing special about it. We're not even adding anything to this outline. And in this scenario, we even do a tail to dev/null just to run as an example. And so what we do is we have a name, the NSC VPP. So this is the name of the service or of the client that we're adding in. But the thing that I want to point out is in the annotations we have network service mesh.io listed as an ICMP responder. And so with this particular line, the network service client will actually spin up and use this particular service. So in the code, let's see if I can expand this out as well. So if we go to examples, cmd, nsc, nsc.go, so this is actually where the code that ends up running is it spins up a new client, and then it asks it to connect to whatever that label was attached to using a kernel interface. And so this is pretty much all that's necessary to get that initial client. So in terms of the going back to the Kubernetes side, let's take a look at one of the ICMP responders. So we have Kubernetes conf, and let's pick ICMP responder NSE. So this one has a little bit more attached to it. So we have some pod affinity information, which tells Kubernetes how to where to run these things. But the important ones is, in this scenario, we've added them in as environment variables, but they don't have to come from environment variables. So this gives it the name, the ICMP responder, tells it to enable tracing, what set of IP addresses do I want to allocate from this? So the IP address will get allocated, and then it'll respond back with the IP address that's selected. And so we actually use these in order to drive it. And so let's make sure the pods are all up. Okay, so let me connect to Skydive. And so Skydive, let's see. Connection refused. Oh, that's right. So what I'm going to do is I'm going to make Skydive port forward. So let's go ahead and copy this over. So Skydive port forward, and now we have port 42. So we refresh this, we can see Skydive. And so this particular system will allow us to view the topology. So let's expand out and see what's in there at the moment. So this one, this one's a little bit difficult to see. Let me see if I can zoom this one in. So this one is Command plus. Okay, so can people read this? So in this scenario, what we've done is we've said, like, this particular system is using Docker. The name is Kubernetes Jaeger. This is the network namespace that's attached to it. That we can further expand it out. And if we expand it out, you'll actually see information about each port. So example, if I can get it to stop moving for a second. It's because I zoomed in. So you can actually look and get metadata about the actual devices themselves. So this one is ETH0. You can see the IP address of those systems. So this allows us to see what does it look like at the moment. So let's go ahead and reshrink these again, so that way they all end up on the same system. So the next thing that we're going to do is we're going to do ICMP, Kubernetes ICMP deploy. So this is going to deploy a Kubernetes pod. It's going to deploy the ICMP network service endpoint. It's going to deploy the client. So we can see that they're starting to it's starting to spin up a couple extra pods, and we're actually going to see connections come up between them both. And since this is a bit small, so I'll read off what some of these things are doing. So here's one that was created. So in this scenario, this let me go ahead and refresh this. Okay, so with this connection between the network service client and endpoint, we'll look at the data, at some of the data. We have source, and it gives us the IP address 10.21.9/30, and this is a private network. There's actually multiple systems that are attached to it. Let me reduce them and expand them out again, hopefully. So this is actually written by some of the colleagues over at Red Hat. It's a very new product, so they're still working out some of the visualization stuff on it. Via, so this one is actually hooked up using VXLAN with the auto-negotiated system that we described before. And you can see the destination, source, and IP of those systems, and the VNI was auto-selected to 3. And you can see information about the destination. The mechanism type in this scenario is a kernel interface and has some parameters about it as to how that works. So in this scenario, we actually have a couple ICMP responders that we created that are they're created. They're private networks between those particular pods. And what we can do with them is, let's go ahead and take a look at some of the pods. Let's go ahead and go to, let's try this one. And so we'll say control exec IT, and we'll take a look inside of it. So we have, so this one has an address of 10.40.0.05. So is this the right one? No, this one is Vpp Agent, so I needed to pull it. That's actually a shared memory one. I apologize. I needed to pull up one of the standard ones. So NSC VPP. So we'll pull up one of these. So the reason why the IP did not show up in that one is that one has actually shared memory. So there is something connected to it, but it's harder for me to demonstrate shared memory at this point than it is to demonstrate a kernel interface. So let me go ahead and bring up so we see we have an NSM one that's listed here, and with an address of 10.21.5, and there should be other systems that are attached to it. So there's a system 10.21.6 that was assigned to it, and it's pinging that particular system in the ICMP responder. So in short, that's it's showing the connectivity was made between them. Okay, so let me go ahead and get rid of the ICMP responder. So we'll delete the ICMP ones. We'll see those connections start to go away. And for the next one, we're going to do this one we're calling we're calling it the VPN one or VPN demo. It's not a VPN yet. It's going to turn into a full VPN later on. So this is the basics of it. But one of the things that's interesting with it, let me go ahead and add the make Kubernetes demo onto this, and we'll make sure those end up in the Etherpad. So make Kubernetes VPN deploy. And so with this one, once it's up and running, let's take a look at what it's starting. So we see the pod is created. We see that there is this one here is the VPN gateway, and this one here is listed as the client. So these connections are made using, this one's Veth pairs, this one, there is no mechanism there because it's actually memory interface on one side and it's kernel interface on the other. So this one has an IP address of 10.60.1.2 for the destination. So this one should be 10.60.1.1. Let's see if we can verify that. The source is 10.60.1.1. So let's go ahead and get pods. And what we'll do is just find which one it is. VPN gateway NSE. So we'll start with the kubectl exec IT, and then we'll do the VPN gateway. So you're going to have to work out what the right one is for your system because these are all random. So go ahead and copy that over to here. And then what we'll do is we'll take a look at the IP addresses. So we verify 10.60.1.2 is the one that it loaded. And we actually don't have curl on this one. So this one is actually running Nginx. And so what we'll do is we'll check port 80. You can see that it's running. And we'll check port 8080, and you can see it's running there as well. So we have attached to that, we also have a firewall. So we go to Kubernetes configuration, and we have Vpp Agent Firewall NSE. Write it anyway. So we can see in here, if I can find the right spots, is two actions. So we have allow ICMP and allow TCP port 80. But notice there's no allow port 8080. So this gets wired into the firewall endpoint. That in this scenario, all the firewall endpoint does is it then will connect to VPP, and it'll then add in these configurations directly into the data plane in order to get you the things that you want. So what we'll show off in this scenario then is, let me show off the pod. And so we'll do kubectl exec IT. And inside, we can see the 10.60.1.1, which we saw before. And we can ping the remote system. So this is pinging the remote system. If we need to install curl. So if we take a look at curl 10.21.1, 10.60.1.2, we see port 80 worked, which matched our which matched our firewall rules that we saw before. We saw ping work before. But if we try port 8080, you can see that port 8080 doesn't work. So it matches the firewall endpoint in this scenario is filtering out that data. So in a nutshell, that's network service mesh in action. So in terms of, are there any questions on any of this topics or this material? So yeah, so I'll stick around as well. So we're coming up close to the end. So if you would like to get involved, there's a couple things that we have. So the first one is we have a lot of information on networkservicemesh.io. We have a GitHub network service mesh is network service mesh on GitHub. And so we have weekly meetings every Tuesday at 8 a.m. We have now actually a documents working group, and we have a use case working group. So if you want to, you don't have to be a programmer to help. Like if you want to contribute with use cases or documentation or some other thing similar, we can definitely use all the help that we can get on that. It's a very new project, so we've been alive less than, I think we should be hitting our 1-year anniversary about now. So it's very, very new. And we already have people in our meetings from, usually our meeting attendance is around 20 people. We have people from companies like Cisco, VMware. We've had people from Red Hat. We've had Huawei, AT&T, or people from Orange actually contributed the Skydive stuff that you saw in there. We have people from Bell Canada helping out. Charter is driving, guy from Charter is driving our documentation stuff. So feel like there's a lot of activity that's going on, and so it's just a matter of like if there's a use case that's important to you that you think maps really well to it, like come over and have a conversation with us. Even that is useful.
Where are these?
What's that?
Where are these?
Oh, they're all held online on Zoom. So we have
Online.
yeah, so they're online. If you go to the Network Service Mesh GitHub page, there's a link at the top that says weekly meeting minutes. We had a meeting today, but it was a bit smaller because everyone's traveling here. But you see some of the larger ones over time. We have, and not everyone adds themselves to the list, so that's why they're a little bit smaller too. But we keep really detailed meeting notes as well. So you want to see what's going on. Even if you can't attend the meetings, it's worth looking at the meeting notes. And we have a link to the bridge details at the top of the meeting notes, so you can join this. All the meetings are also recorded, and so if you want to actually watch and see what was added, CNCF actually posts it onto their website. And the funny thing is we're not even a CNCF project yet, so they're providing us a huge amount of help. That being said, next week we're actually going to propose to the CNCF talk to see if we can become a CNCF project. So this time next week, that status may actually change. And so with that, are there any other questions? Sure.
So is this a graduated project?
No, not graduated. We want to become a sandbox. We're too early to graduate. So is there another question?
But it's not Istio, right?
No, it's not Istio. In fact, Istio is not a CNCF project. So Envoy is, but not Istio. I'm hoping that Istio will eventually contribute in their project. I believe they said they eventually will, but I guess they're not feeling ready to yet. So, and yeah, ultimately it's up to them. So, sure.
What are other examples of use cases you can solve with network service mesh?
Okay, so other examples. So we didn't go over this specific one, but we are looking at like how do you get something like full kernel bypass onto a system. So what I mean by full kernel bypass, it could be one of a couple things. Some examples include shared memory from your pod to your data plane, and then your data plane could use DPDK or something similar to get direct memory access to your NIC card. We're also looking at how do you connect to a top-of-rack switch that provides you with a very specific thing using something like SRIOV. We're also looking at if you have a VNF, a virtual network function that's running in OpenStack, then the gRPC, the APIs that we have in gRPC are all generic. They actually don't require Kubernetes. And so that means, and in fact, you can actually implement, as long as you implement the registry, you could implement the APIs themselves and run everything on OpenStack or run everything on your own infrastructure without Kubernetes. And the protocol should still work. So this allows us to do things like we wire in a Kubernetes. Maybe you want to do a shared memory pod to your data plane. Your data plane then does VXLAN with hardware offload to maybe some OpenStack system, which then runs your firewall and a VF, in your VNF, and then from there does whatever it's, connects into the next thing, maybe some top of rack switch. And so what we're trying to do is be two things. Number one is to be a matchmaker. We want to match things that want connections to things that have connections providing some service. The second thing that we're doing is that we want to be we're calling it a controller of controllers. So we're not the thing that is your data plane. We are the thing that will connect you to your data plane, and we will help you negotiate those parameters across it. So you think of it like a controller of controllers. And so data planes, like in my opinion, data planes are incredibly difficult pieces of software to work. I don't want to replicate that. I think there's some amazing work that's coming out of multiple communities. And so trying to replicate that work doesn't make sense to us. So our idea is like, you have a firewall, you have a VPN gateway out there, you have a data plane that meets your needs. Go use it, and we'll help you connect to those things and bring the control of that to a cloud native environment. Sure.
So you mentioned control plane. Do you manage multiple control planes, and can it become usable for edge networks?
Yeah, it could be multiple.
Like if I have a ONAP
Mhm.
as a major global controller, can I tie that up to connect to multiple control planes? I think it is.
Yeah, so I've actually seen network service mesh used in two ways. So one of them is at the top, like you install it at the top, connect. You could say one ONAP to another ONAP, or one Kubernetes to an ONAP, or something similar. The second way that I've seen it used is some vendor. One path I'm seeing is a vendor sticking their API at the top, but then internally using network service mesh to actually drive the connectivity as well. So I'm actually seeing both patterns. The second one really surprised me because I wasn't expecting anyone to do it this early, and now there's someone who's actually looking at that. But yeah, in terms of the network, I'm actually expecting the main use case in the beginning to be how do you get fast data access within Kubernetes to something that you want, and the second one is how do you cross the divide from like Kubernetes into OpenStack. So I think some of those earlier use cases will be very helpful.
I would be surprised if you did SD-WAN also included in that.
Yeah, I think so as well. So, and another thing is most of the use cases either fall between like enterprise or telco. So some of the ones I mentioned were telco. The VPN use case I showed off just now is clearly enterprise, and so I think there's going to be a mixture of both types of environments. So it's just a matter of like this simple pattern. What would it make sense to apply it to? And then that would be like the question to like what are the potential use cases? And part of my job as being part of the community and trying to drive some of this stuff is to make sure that when someone comes up with us with a use case, that we tell them whether or not, like, if it's not a good idea, if we don't think it's going to be a good mesh, it's actually important for me to actually say that as well. So it's important to not say we're going to gobble up all the use cases. So one good example is like we don't want to replace Calico, we don't want to replace Flannel or so on. There may be ways we can help augment them and give them some additional benefits, but we're not trying to replace like your CNI driver. We're not trying to replace like you may have other, like we're not trying to replace the SDN itself. Like we'll still hook you up with an SDN or so on. Like Open Daylight's a good example where Open Daylight's looking at implementing, and they've started to work on implementing some of our APIs. We're not going to replace netconf for them. Like they can still use netconf, and netconf is actually a great way to connect into their white boxes. We don't replace OpenConfig or Yang or so on. So we're trying to just solve like a very simple problem, which is getting that matchmaking, getting that negotiation connected between two systems.
More of the automation space.
What's the question?
More of automation space.
Yeah, a lot more on automation. and just getting at that API. Because if we get that common API, we stop fighting over APIs, and then we actually, the competition then becomes who has the best implementation for your use case. So who has the best firewall based upon your use case, or who has the best. And so the idea is to try to drive it from that side, and also makes it easy so that, like I didn't talk about it in this scenario, but because we're controlling the connections, if a connection dies, we know about it. So we can then auto heal those connections for you, or give you the power to realize, hey, this connection's dropped. Maybe you want to do something special with it. So the ability to auto heal or to upgrade by policy or so on are additional benefits that we'll be able to drive through this as we start to mature. So your VPN goes down, no problem, wire another one into you. Or maybe you want to have load balance VPNs or something like that. Like we can help make those things by policy, and if the policy changes, then your topology changes with it. So, sure.
Just on the same site, one location, do all tunnels lead to that?
I don't know. I hope not.
That's the impression I'm getting, but I keep hearing about tunnels all the time. You mentioned it.
When we say tunnel, we say in a very loose term. So not everything is. Well,
You should never use them unless there's going from one site to another site.
No, flannel, things like flannel and so on, you continue to use them. Like same system to remote system. They solve the Kubernetes networking for Kubernetes specific type of networking. And so they make that particular style easy. And so, in fact, not all Kubernetes networking systems are tunnel based. So if you look at Calico does not use tunnels as part of its setup.
You got
Canal has been interesting because Canal is Kubernetes policy mixed with flannel for the connectivity. So it's Calico policy and flannel connectivity. But
I don't see any reason why you use them unless you're walking from one side to the other side.
well, flannel people want to bring flannel because it's a very simple system. So it also was one of the first ones out there. So flannel was originally the reference architecture for CNI. So flannel got a lot of use from that as well. It's a very simple system, very easy to work with. Calico is also simple as well. And Calico does route manipulation rather than creating tunnels and encapsulation. And that's actually really important if you're trying to do networking in, like if you have a VXLAN environment, you're already running on, let's say, OpenStack. You don't want to stick like VXLAN on top of VXLAN. You get significant performance issues. So you bring in something like Calico, and Calico does route manipulation. Your VXLAN still works like VXLAN. You don't get double encapsulation. And so you end up with performance increases as a result. So in terms of network service mesh, that's up to the operators as well. So the operators have to make sure, it doesn't prevent them from doing bad decisions. They still have to set up like good decisions and choose a good encap or choose a good forwarding mechanism or so on. So it doesn't alleviate them from that. But once they make those decisions, and then they can apply them as policy, and then we perform the connection and help do the negotiation from in a more automated way. Any last question? Because then we have to finish up. Sure.
Where do I find a roadmap?
Oh, roadmap. That's a great question. I'll get the documentation team to get us a roadmap. I'll tell you what the roadmap is at the moment, though, at least from a high-level view. So we want to get an alpha version of this out for Cubekon EU, which is in May. We want to try to get this into a production environment or production quality, hopefully by Cubekon North America, which I believe is around the end of November. So in terms of the roadmap, we're going to focus a lot on quality over the next couple of months. And we're also going to focus on, like, we're hoping to convince some other data planes, because right now we're focusing primarily on VPP as the data plane, because we have FIDO people involved. But we also are trying to work, like, I've been coordinating with like some of the Tungsten Fabric people, and they've been flat out busy because they're getting ready to do their next release. So once they're done with that, I'm gonna circle around with them and see if we can get Tungsten Fabric listed in there. We have some people from VMware who are contributing, and so I'm expecting them to eventually have an OVS driver on there. And so over time we'll get more data planes attached to it, and there's some more companies who are also starting to look at providing their own data plane stuff as well. So specifically with OVL and some of the top of rack switches and white boxes and so on. So yeah, so there's a lot of, so in short, that's what the roadmap sort of looks like. It's a bit loose right now because it's still, like, we have people working on it, but no one technically, there's no like controlling organization, controlling group that says, you know, this is like a startup that's paying for this or so on. So the roadmaps are more open source style, like, hey, we're going to get a release version. This is what we mean by release quality, and we have people from, like I mentioned, Cisco and VMware and so on. So we'll make sure that quality is high, but we want to be careful on what we promise to deliver because right now we have so many people. We don't know whether we'll have double that or we'll have half in 6 months or so on. So we need to remain some level of flexibility. But yeah.
How engagement with Cisco and other network vendors in this project?
Last I was told, between the lot of us, of everyone involved, we have around 8 full-time people working on it at the moment. So there's some decent engagement. Of course, it's still an early project, so there's no company that's going to say, we're fully backing this at this point, because there still needs to be a lot of work. My hope is that as it continues to move on, that we can get them to say, hey, we also support network service mesh as a way to connect into this thing. And gives them an easy way entry into the system. Great, so that's the end of my time. Thank you.